let's come back together and kind of see where we're at on this one. Part of the reason I put this together as a warm-up is these are basically the two main concepts we've looked at. Last week we looked at graphing, and this week so far we've looked at the idea of applying, especially with money type of examples or population, those types of things. As I just kind of went around and checked fairly quickly just to kind of see where everybody was at, I did notice there was quite a few people that were struggling on the graphing part of it, so I want to make sure we definitely go over that and just refresh your memory on that part of things. So if I focus on that part here first, okay? First part of this, let's go through. I'm going to identify the different pieces that are in this equation. First part, what's the value of A in the equation? What do we have? What's my A value? Kyle, what is it? 2. It's the 2 that's sitting out front, okay? Now, keep in mind, if there's no horizontal or vertical shifts, which in this case there are, A normally is your y-intercept, okay? So I'm going to put that kind of in here. This is like your starting y-intercept. And that's what's going to get shifted then with our horizontal and vertical shifts. Okay? What's my B value on this graph? Or in this equation? What's the B value? Elias, what is it?
2.
Yeah, it's also 2, which tells me what about the graph? What do I know based off of that B value? What do we think? What do we think? Come on. What does B tell you? What is it? No, that's the A value. A is the y-intercept. B tells you what? That's your multiplier. And so in this case, because your multiplier is bigger than 1, this is going to be exponential growth. So you know that you've got an exponential growth on this one because of that B value. Okay? If we keep going, if we identify H and K, what's H on this one? What's my horizontal shift? What do you think? Yeah, Parker?
-1.
That's the vertical shift. So the K value is -1. What's the H value? Do I have one? No, I don't. So H is actually 0. And what I'm looking at in this case is I'm looking up here at the actual equation. There's nothing else up with the x in the exponent. There's no x plus something or x minus something. That's the value of H. The -1 at the end, that's your K value. That's what shifts everything up and down. Okay? So now if we start to put this together then, normally, and don't go ahead and draw this yet, but normally, like I said, your A value would be at 2. So normally I'd say, all right, there's my y-intercept. But these two pieces right here, H and K, are going to take that information and shift everything, okay? Now, I'm not going left or right at all, but I am going to take the K value and it's going to drop down 1, okay? So in this case, that point actually comes down here to a +1. There's your first point on the graph. You would normally have your y-intercept at 2 in this problem, but because there's a shift down 1, it actually comes down to 1 instead. Okay? Which means, by the way, right away, if you remember, let me put this in a different color here. If you remember then, horizontal asymptote is normally at 0. That also gets shifted down 1. So now, I know that I've got a horizontal asymptote at y equals -1. Okay? Because normally it's at y equals 0. The shift moved everything down 1. So there's the graph that I have so far. And now the rest of this is just find some other points that are on the graph. Okay? Pick a couple values to the left. Pick -1, plug it into the equation, see what you get. Pick +1, plug it into the equation, see what you get. And just plot a few other points. Okay? So the rest of this problem is take your make an XY chart, and plug some values in to either side of our starting point. Okay? So, as we take a look at this, I'm going to kind of skip that part of it only because I want to keep things moving since we have a little bit short on time. But like I said, the rest of this, take -1, plug it in for x into the equation, get an answer. Take -2, plug it in, get an answer. It doesn't matter what you plug in, as long as you know that we're going to have kind of that exponential growth, and therefore at least a rough sketch of the graph would look like something like this. there would be kind of your graph. It would approach your horizontal asymptote here, and then we know it's exponential growth, so I know it goes through that point. Okay, that's at least a very rough sketch of what's going on. And that should help when I had you take I told you to take out that other assignment from yesterday. This warm-up should help you on that assignment because there was some review of graphing on there as well. Okay. All right, then if we take a look at problem number 2 here, this is a review of the last couple of days. If you invest $2,500 now into a savings bond at 2.5% interest, how much will it be worth in 10 years? First question I have for you, is this one of those PERT problems or not? There's a simple clear, you say no, why not? You're right, by the way.
It doesn't have the continuously.
That's exactly it. And that's one of the points I wanted to make today with this warm-up that maybe I made yesterday, maybe I didn't make clear enough. But the idea is the only time you use that PERT formula is if it's compounded continuously. If the clock is always running, then you're using that PERT formula, okay? Otherwise, we go right back to our normal formula here. So, y equals, a value in this case is our starting point, 2,500, times 1 plus, okay? Plus, because of the fact that the money is going to be increasing, again, it's going to be growing. What's the decimal that I put down then? 1 plus what? What is it? Just take here. 0.025. Remember, you got to take the 2.5% and put it as a decimal. So it is 0.025. And that whole thing then will be raised to the 10th power. Okay? Whole thing is raised to the 10th power. And at this point, then you just plug it into the calculator. What'd you get on this one? Somebody help me out on this one. What'd you end up with for an answer? How much money do we have 10 years later? What'd you get? Abby, did you get it? What'd you get?
$3,221.
$3,200.21. Okay, agreed? Other people confirm answers? Yep, all right. And there you go. So $2,500, 10 years later at 2.5% interest, $3,200 about. Okay, you gained a few $100s. Any questions on that at all? Like I said, these were probably the 2 main ideas from the last week and a half. Okay? Graphing exponential functions and being able to come up with some applications of them. Okay, so let's go into what we're going to do today then. Actually, let's go to the homework. So if you haven't taken this out yet, go ahead and take this out. There's one specific section of problems I wanted to talk about quickly. And then if you've got anything else, you can we'll go from there. Notice first, by the way, like I was talking about in problems 5 through 8, hopefully now, after talking about the warm-up that we just did, if you were struggling on problems 5 through 8, they're just like the warm-up that we were just doing. Identify the A value, identify the B value in terms of the graphing stuff, so that'll take you back and review some of that stuff. Okay, so that should help with that. The specific problems I wanted to talk about are not necessarily long or difficult in terms of math, but there are quite a few people that have turned this assignment in that were struggling. And what I want you to take a look at is problems 14 through 17. Okay, 14 through 17. People seem to be struggling on the growth or decay factor. So when you're asked for the growth or decay factor, what you're being asked for is your multiplier. What's the multiplier? What would the B value be? So in this case, if something's going up by 45%, if you go back to like what we were just talking about, what you then have really is 1 plus 0.45. Meaning your multiplier or your growth factor would be 1.45. Okay? That would be your answer for that problem. 1.45 is what you'd be your repeated multiplication. If it's going down by 10%, you would have 1 minus 0.10, which leaves you with a multiplier of 0.9, okay, or 0.90 if you want to look at it that way. Okay? So you're multiplying by 0.9. And if you think about this, I'm going to give you just a different way of thinking about it real quickly to see if it makes sense, if it's a connection. If you're adding 45% to something, what that means is, let's say 1 year later, you then have 145% of what you had last year. That's where the 1.45 is coming from. That's why you're doing 1 plus or 1 minus. You're either, it's going above 100%, meaning it's going up, or you're going below 100% and it's going down. 0.9 as a multiplier means you have 90% of what you had a year ago, which means you have less. Okay? If you think about the next one, if we're going down by 40%, that means our multiplier is 0.6. There's 60% left. Okay? And you can think of it as 1 minus 0.4, which leaves us with 0.6 as our multiplier. Does that make some sense? You get the idea? Like I said, it's not necessarily hard mathematically, but some people were struggling as they were turning this stuff in. There were quite a few people that were off on this section. What about, we might as well finish this off. What about the 200%? What would the multiplier be if it's going up by 200%? What would you be multiplying by? 3. Very good. Because you would be going with 1 plus 200% as a decimal would be 2, which means your multiplier is 3. Okay? 3 times the amount. Means it's going up by 200%. Make a little bit of sense, hopefully. Clear some things up for you. All right. Any other questions you have from this assignment before we move on? For the most part, at least of the people that had already turned this in, most people seem to understand and do pretty well on the rest of it. A little bit of struggle with the graphing, a little bit of struggle with this stuff, and so hopefully we've got those cleared up. All right, let's go to the notes then. So let's get into the actual lesson today. You can see here is, let me go back to the objective here for a second. Objective for today is we're going to introduce something that you have not seen before. You probably have no idea what it is. It is what are called logarithmic functions. Okay? We are trying to evaluate, we're going to introduce something called a logarithm and try to explain what that is and how you use it and go from there. Okay? So, if we get into the actual lesson for today, here's kind of the first idea. If we're talking about logarithms, we talked before break that we talked about inverse functions and that kind of stuff. So for example, that's where this is going. If we see addition, then what would we do to move it to the other side if you're solving an equation? What's the opposite of addition is really what I'm getting at. Subtraction. Okay? So we would have subtraction. Hey, come on, Bill. We just started. So if you got addition in the equation, you use subtraction, the inverse operation, to solve. If multiplication is in the equation, what do you do to solve? What's the opposite? Division. Okay, so we've got division here. If you've got a square root in an equation, how do you get rid of a square root? What's the opposite? We square it. Okay. What if you've got cubing something in the equation? How do you get rid of something cubed? Cubed root. Yep. And here's the introduction. Anytime you have something, what's called exponentiation, whenever you've got a variable in the exponent, in order to undo that, the inverse operation is you use what are called logarithms. Okay? Just like square roots and squares are the opposites of each other, they undo each other. Exponentiation and logarithms, that's what a logarithm is. It helps undo when you've got a variable in the exponent. It'll kind of bring it down into the actual problem so you can solve for it. Okay? So that's what we're looking for. That's kind of at least what a logarithm does. So let's do a couple of quick lead-in examples here, just to kind of start getting you the idea. So first question, 2 to the x equals 8. Let's do this in our head. What does x equal? There's an exponential function. We got a variable in the exponent. 3. Okay, 2 to the x equals 3. 4 to the x equals 16. What is x? 2. 3 to the x equals 81. 4, yep, 3 to the 4th power is 81. 10 to what power equals 1,000? Nope, not 10. 10 to what power? You're thinking multiplying. 10 to what power?
3.
3, there you go. Remember 10 squared is 10 times 10. That gets you to 100. 10 cubed would be 10 times 10 times 10. So this one would be 3. And so the question is, when I say what did you ask yourself on the last 3 questions, and really on all 4, hopefully you were asking yourself, all right, 2 to what power is 8? 4 to what power is 16? 10 to what power is 1,000? That is exactly what a logarithm does. If you take a look, that is exactly what a logarithm will do for you. It will answer these questions. Okay? Here's what we're going to take a look at. I'm going to do this a little bit differently than what I was talking about, but here's what we're going to take a look at. If I go back to problem number 1, we're going to add in a calculator here in a second. And let's say I rewrite that and I take a look at this as the log base 2 of 8. Okay, notice the 2 and the 8, they're still in there. And if now I bring up the calculator, so if you notice on your calculator, there's a couple of different buttons. One of them is this LN button. Okay, this one right here. Oops. Right there is an LN button. We're going to talk about that later on. Okay, but for now, if you notice, there's this log X button. That's the one that you're going to be using on your calculator. Okay, so if we go through and we take a look, if I plug that in, it gives you a spot where you can plug in what the base is. Okay, that's the bottom part where the cursor is right now. And then it gives you a parenthesis of what are you actually taking the log of. Well, if you notice, if I put in the log base 2 and I plug in 8, notice what you get. You get 3. You get the answer to the problem. 2 to the x equals 8. Well, log base 2 of 8 happens to be 3. Let's say we do the next one. If I were to go through and rewrite this one, 4 to the x equals 16. Well, let's say I went through and said log base 4 of 16. Again, both parts of that exponential function, now I'm kind of turning it into a logarithm. If I go back to my problem and we change the parts, log base 4 of 16, I hit equals, and sure enough, there it is, x equals 2. How would I rewrite the next one? If I was going to put it in what's called logarithmic form, like we've been doing, how would I rewrite it? What would I do? Based on what you just saw in the first 2. Log? Yeah, Parker?
Log 3 and then
Yep, the log base 3. So now, if I start breaking this down for you a little bit, the number that's kind of the subscript, the one that's a little bit lower, that's your base. Okay? Base of the log, base of the exponential function, always the same. The bases stay the same. So that's your base, and then the number, whether it's the 16, the 8, that's what you're taking the log of. That's called your argument. That is the actual name for it. And so in this case, just like Parker was talking about, I would do log base 3 of 81. And now if we plug that in, just to kind of confirm that we did it correctly, log base 3 of 81, we hit equals, and sure enough, there's the 4 that we were talking about. So there kind of confirms what I said down below. A logarithm will solve these problems. Now, you might be thinking, well, I don't really need a logarithm to solve this. I did all this stuff in my head. But what if the question was, instead of 3 to the x equals 81, what if it was 3 to the x equals 70? Now, there is not a nice number. You can't take 3 to some nice power and get 70 as an answer. There's still an answer, it's just not a nice answer. That's where logarithms come in handy and they start working a little bit better. Is you can go through and take those logarithms of those not so nice things that you can't do in your head. Because even though there are some, most of them going forward you're not going to be able to do in your head. Okay? So if we take a look, let's keep going. This is just kind of a quick refresher. As we go through and we take a look, remember back to before break, we talked about inverse functions. And this is just a quick refresher that remember an inverse function undoes the other. Remember when we talked about switching the x and the y's? Okay, so if you notice, The example I gave you was y equals x squared plus 4. That's the red one. Go through and do the inverse function. You end up with a square root function, and therefore there's your inverse function. That's just kind of a refresher. Well, if you then take a look at the next slide, there's how it relates to exponential functions and logarithms. So notice the one in red is the equation y equals 3 to the x. That's the actual graph of y equals 3 to the x. And again, you could go through and we could find the inverse function. Here's what the logarithmic function looks like. Okay? Remember there was that reflection over the line, that diagonal line, y equals x? Just to kind of, I wanted you to see it. We're not going to spend a lot of time, we're not going to graph logarithmic functions. Okay? We graphed exponential ones because those are fairly realistic. There's a lot of real life type of things. But we're not going to graph. I just wanted you to see the inverse, the idea between exponential and logarithmic functions on a graph. Okay? That's as far as I want to go with that. All right. Let's take a look. Here is the main, literally the main idea of today, right here. This is what we're going to be practicing. And we kind of have already done it. The definition of a logarithm is right here. This is the main idea. This is what we're going to practice today. We're going to practice it some more tomorrow, going back and forth between exponential and logarithmic form. So if you notice, first one is in exponential form because we've got the variable and the exponent. Okay? There is the logarithmic form of the same thing. This is what we were just doing when we did like log base 3 of 81. What I want you to notice, again, we just highlight some of the parts. The base of the exponential function is always the same as the base of the logarithmic. Okay? Just like we did, just like we talked about when we were doing that. In this case, whatever the exponential function equals, that's what you're taking the log of. That was like the 81 or the 16 or something along. That's your argument. That's what's called your argument. And the variable, or the exponent, is what you're always, the answer you're always going to get. What the logarithm will give you, it always gives you the answer, the exponent. Okay? And notice there's a couple of stipulations here. These are mainly coming from what we talked about last week. So notice it says b and y have to be positive numbers. Well, you can't take the log of a negative number. Here's the reasoning behind it. We said before, for an exponential function, you have to start with something in order for it to either grow or decay. So we had said before, b has to be positive, but can't equal 1. That's where this stuff is coming from. And therefore, by default, if you take a positive number and raise it to a power, you're always going to get a positive answer. So by default, y is going to have to be positive. Okay? If you start with a positive number and raise it to a power, your answer is always positive. Okay? So these definitions or these restrictions are really coming from the exponential side of things that we talked about last week. Okay? But this is what we're going to do today. We're going to go back and forth between logarithmic and exponential form, because the better you get at this, the easier this chapter becomes as we move forward. Okay? So let's take a look. So if I want to rewrite these in, so now I gave you some, now we're doing the opposite of what we started with. If I want to rewrite these in exponential form, okay, we're already in logarithmic form. This one we kind of did the other way. Easy place to start. The base of the log is the same as the base of the exponent, so I know it's going to be base 3. What power am I going to be raising this to? The 4 or the 81st? Which one's the power? What is it? 4. Yeah, it's the 4. 3, so the 4th power equals 81. There's the exponential version of the exact same thing. Okay. There's your exponential version of that exact same idea. 3 to what power gives you 81? No, 4. Same idea number 2. Start with the base. 9 to what power gives you 3? Well, if we rewrite that, let's 9 to the 1/2 power will give you 3. Because, let's go back to chapter 6 again for a second. What's the 1/2 power? When you take the 1/2 power, that really is what? It's the square root. There you go. So then the 1/2 power is the square root. Remember back, top number's power, bottom number's root in a fractional exponent. So 9 to the 1/2 power is really just the square root of 9, which is 3. Okay? Then if we go through and we do one more here, if I rewrite this in exponential form, start with the base. What power am I going to raise this to? Which one of those is the power? -3, yep. Equal to, in this case, 1/8. Why should that make sense, by the way? 2 to the -3rd. How do I get 1/8 out of 2 to the -3rd? Yep, because it's a negative exponent. Remember, that creates a fraction. Remember back to that last chapter, you take this and it drops into the denominator. And 2 cubed is 8. Okay? The negative exponent turns it into 1 over, and then you evaluate to get 8 in this case. How we doing, okay? Alright, let's keep going. Now we're going to go the other direction, which we kind of did already. If we rewrite this in logarithmic form, so in this case, we're going to start with the log. What's the base of the log going to be? 3. Base of the log, base of the exponent, same thing. And then really the question is, the other numbers, which one goes where? Yep, the 9 comes after the 3. Because really, if you think about it, at least this is the way that I think about it. Okay? I think to myself, what power do I raise the base to get the argument? It's right here. 3 to what power is 9? Okay? And that's why, remember, the exponent is what you're always getting as an answer. So that's what it's always equal to. Equal to 2. 3 to the second power equals 9. If we do this one, log, what's the base? 3. Yep, log base 3. If I set this up, 1/9. Yep, very good. I'm going to actually put that in parentheses. You don't necessarily have to, but I'm going to just make it clear. And then equal to -2. Again, 3 to what power gives you that? It's right here for you. 3 raised to what power will give you 1/9? Well, the power is -2. Okay? All right, let's keep going. We doing okay? All right, let's see if you can do some of these in your head. See if this is making sense. We started off by doing some kind of lead-in examples, what 2 to the x equals 8, 3 to the x equals 81, that kind of stuff. Now we're going to do logarithmic examples. What's the log base 3 of 27? Log base 3 of 27. What do you get for an answer without using a calculator? 3. Why 3, Bella? What were you doing in your head? Yeah, right here for you. What power do I raise the base to get 27? 3. That's where the answer is coming from. How about the next one? What power would I raise 4 to get 1? Was it, Jack? 0. Very good. In this case, you end up with 0. 4 to the 0 power would give you 1. Okay? How about the next one? 1. 5 to the first power gives you 5. How about the next one? Careful. Why is this no solution?
Get a negative.
You can't take the log of a negative answer. You can't take a positive base, raise it to a power, and get a negative answer. There's nothing that you can take 6 to and get -1 as an answer. So we can't take, that goes back to kind of that definition. We can't take the log of a negative. How about the last one? This one's a little bit tricky. 5 to what power gives you 5 to the 2/3? Don't overthink this one. Close. Just the 2/3. 5 to what power would give me this? Well, if I raise 5 to the 2/3 power, I get 5 to the 2/3 power. And so you're just missing the power is the only part on that one. So that one's a little bit trickier. This one will become a little bit more clear as we move into as we start adding some properties and things. This will start to become a little bit more clear as we go through that. All right. Last thing we need to talk about is this. There are some special logarithms whose base is so frequently used that we give them some special treatment. And in this case, what I'm referring to is this. So just like when you have x, for example, you don't normally write the 1x in front of the 1. You just know it's there. If it's x to the first power, you don't really write the first power, you just know it's there. A couple of things with logs as well. A log in general, it's called a common log, are normally base 10. Okay? Those are the most common logs because our number system is in a base 10 number system. And therefore, if you just see the log of some number, okay, for example, let's say I said the log of 20, and there's no base that's written, it's assumed that you know that it's base 10. Okay? That's what I'm getting at right here. So if you don't see a base, it's assumed to be a base 10. Technically, there's a little 10 sitting right there. Okay? So just a heads up on that. The other part, I told you earlier on the calculator, there was also this LN button that was on there. That is what is called a natural log. And if you remember, in the PERT formula, we introduced this idea of E. It's the exact same thing. The only difference is if you change the base from 10 or 2 or 3 or 5 or whatever, some random number, if it's a base E logarithm, that's what's called a natural log. Okay? So you've got common logs and you've got natural logs. Whenever you're dealing with E, you're using natural logs. That's the only difference between those two. It just happens to be that specific base. Okay? And your goal for today and tomorrow, I'm going to have some more practice for you tomorrow in general. We'll add a little bit to this, but probably not a lot. Your goal is to continually be able to work back and forth between the two forms. Okay? And the assignment that I'm going to give you today is I've got a reteaching worksheet. There's not a lot of problems on it, so I don't think it'll take you a real long time. There's only, well, it says there's 29 questions on it, but it's not, it's the ones where you're just literally writing stuff down back and forth. So there's not a lot of work to do with it. All right, and again, answers are out in Canvas. So please make sure you're checking answers. Tomorrow there will be a very kind of short cleanup lesson, see if you have any questions, and then you should have a good amount of time to get some work done right here in class. By the way, quick heads up, I am going to give, today I'm going to start assigning people for Friday. If you have not turned in a whole lot of homework in the last couple weeks, and if you don't want to be one of those people, you don't want to have to come in on Friday, then make sure that you're getting those assignments in, and if your assignments are in, I'll take you back out. All right, other than that, have a good rest of your day. We'll have fun home. Yeah, what kind of geometry do you need? Sure, I can find something anyway. Okay. Okay. Let me look for some stuff and can I get it to you tomorrow or later today? I'll find something.
All right.
Yes. So on that you can't change the base. So on that calculator, so I would recommend you use the one on the bed. And the one I have up here is the calculator plus half. Yeah, so I would use that because otherwise most calculators you can't use. It doesn't allow you to change to plug in the base. Okay. Something we'll talk about in the future is what's called the change of base formula for that scenario.
I made a goal.
You what?
I made a goal in 12 hockey.
Did you? That a girl.
There was only like 3 on our side the whole